So today we are going to discuss a topic called optical activity. We will be discussing in optical activity the term called optical active compounds. They show a very special isomerism called optical isomerism, that also we are going to discuss. This particular topic may be useful when we study the chapter called haloalkanes and haloarenes, that is the next chapter we are going to discuss. Before we see what are optical active compound, what is optical activity, we should know few terms. So first of all, let us discuss few terms. The first term, the term called monochromatic light. What is a monochromatic light? As the name suggests, mono means one, chrome means color. So single color light is said to be monochromatic light. Single wavelength light is called the monochromatic light. So the light with the single wavelength, the light with the single wavelength is said to be monochromatic light. Like red light, yellow light, blue light, and so on and so forth. Second term we should be very clear about is what you mean by the term unpolarized light, which we can call in Hindi as jungli light, unpolarized light. Ordinary light is unpolarized light. Ordinary light means the one coming from the sun, the one coming from the tube light, the one coming from the bulb, and so on. The ordinary light is supposed to be nothing but unpolarized light. Unpolarized light, as I told you, in Hindi it's called jungli light. Let's see what is jungli light. You know, light is an example of electromagnetic radiation. Means doesn't need any medium for the propagation, and it has a vibrating electric and magnetic field perpendicular to each other. So in unpolarized light, what happens is electric and magnetic field can vibrate perpendicular to each other in any plane. There is no restriction. Like electric and magnetic field, they can vibrate in this plane, they can vibrate in this plane perpendicular to each other, they can vibrate in this plane. There is no restriction. We can have vibration in any plane of electric and magnetic field perpendicular to each other, and definitely perpendicular to the direction of propagation of the light. So unpolarized light is the one which can have vibration in any plane. Vibration in any plane. Vibration of what thing? Electric and magnetic field. So vibration of electric and magnetic field. After we are clear about the term called monochromatic light and unpolarized light, let's talk about what is the polarized light. What do you mean by the term polarized light? That is basically a disciplined light. Disciplined in what sense is that it can vibrate only in one plane. It can vibrate only in one plane. So the third term we can discuss is what is a polarized light, which can have vibration only in one plane. Vibration of what? Electric and magnetic field. Vibration only in one plane. The vibration is restricted only to one plane. Vibration of what? Electric and magnetic field. So let's say we have a jungli light, unpolarized light of single wavelength, that is monochromatic light. We pass it through a prism made up of one of the crystalline form of calcium carbonate called nickel prism. So we take nickel prism made up of calcium carbonate. So when the unpolarized light is going to pass through the nickel prism, depending on its plane, it will allow only one plane vibration to pass through it, and is going to cut the vibration in all other planes. So with the result, what happens when unpolarized light passes through the nickel prism? It will have vibration only in one plane, or it becomes nothing but polarized light. So what is unpolarized light? The one which can have vibration in any plane. What is polarized light? The one which can have vibration only in one plane. Vibration of what thing? Electric and magnetic field, perpendicular to each other. After we are clear about the term called monochromatic light, unpolarized light, polarized light, now we are in a position to see what are optical active compounds. What do you mean by the term optical activity? What are the Then we are going to discuss later on that how do you find out whether the compound is optically active or not? What is the condition for a compound to be optical active? And then we're going to see optical active compounds are the ones which show the special isomerism called optical isomerism. So what we do, let's see what optical active compound does. We use a polarized light. So we have a polarized light. We take a glass tube. In this glass tube we are going to put an optical active compound. Optical active compound like lactic acid. We are going to put optical active compound solution. Let's say lactic acid solution. So what is going to happen when the polarized light is going to pass through optical active compound? You will find the plane of vibration either will tilt towards the right side. The plane in which the light was vibrating, either it will tilt towards right side, or the plane in which it was vibrating will tilt towards the left side. It is going to tilt. The plane of vibration will turn towards right side or towards left side. So what are optical active compound? They are supposed to rotate the plane of the polarized light either towards right or towards left. Those compounds are said to be nothing but optical active compounds. So what optical active compound do is they are supposed to rotate the plane of polarized light. When the polarized light is passed through them, the plane of the polarized light is either rotated towards right or towards left through certain angle. If the optical active compound rotates the plane of the polarized light towards right, the compound is called dextrorotatory. The compound is called dextrorotatory, represented by the symbol small d or with a plus sign. So the optical active compound rotates the plane polarized light towards right, it is called dextro, represented by the symbol d or with a plus sign. If it is going to rotate it towards left, then the compound is said to be levorotatory, represented by the symbol L or with a minus sign. So we have seen what are optical active compounds. Optical active compounds are supposed to rotate the plane of the polarized light either towards right or towards left. They can be dextrorotatory or they can be levorotatory. I have just given you an example of optical active compound like lactic acid, which all of us know is formed in the muscles when we do vigorous exercise. So till now we have seen what is a polarized light, what are optical active compound, and now we are going to see how does optical active compound look like. What is the condition for the compound to be optically active? So it's clear to everyone what optical active compound do. When you pass polarized light through it, they rotate the plane of the polarized light through certain angle towards right or towards left. Now let us see what are how do we find out whether the given organic compound is optically active or not? By just looking at it. This is an experimental method to find whether the compound is optically active or not. Let's see by looking at it, how do you find out whether the compound is optically active or not? Now compound is said to be optically active. The basic condition for the compound to be optically active, which is valid to all types of compounds. A compound is optically active if it does not overlap, or another term for it is superimpose on its mirror image. Does not overlap on its mirror image. It should not have any symmetry at all. It should not overlap on its mirror image. They should be non-superimposable on its mirror image. Let us see a very simple example. Let's say we have got P and compound. We want to find out whether the compound is optically active or not. Suppose this is the compound. What we'll do? We'll make a mirror image. You know what happens in mirror image? Left becomes right and the right becomes left. The phenomena is called lateral inversion. So this is the compound, that's its mirror image. Now you just take like this, put it over here, you will find that this, when moved like this and put over it, they will not overlap. So object, the compound and its mirror image do not overlap. they do not overlap. So since compound and its mirror image do not overlap, if it was a compound, it will be optically active. So if B is supposed to be a compound, since it doesn't overlap on its mirror image, you just move it and put it over here. It doesn't overlap, so that's why it is said to be an optical active compound. Let us see the second example. Let's say we have got B for boy. Another compound, we want to find out whether it is optically active or not. What will be its mirror image? It will be the mirror image. Again, you lift it like this and put it over here. They will not overlap. Since they will not overlap, so this B for boy will also be, if it was a compound, would be optically active. Because what is the condition for the compound to be optically active? The compound should not overlap or superimpose on its mirror image. Let's say suppose instead of B we have A for apple. Suppose we have A for apple. Now you can see A for apple, if it is a compound, it is going to overlap on its mirror image. It is going to overlap on its mirror image. So since these two are going to overlap, this compound will not be optically active. This is an optically inactive compound. If it is. So what are optical active compounds? The ones which do not overlap on its mirror image. So that was a very cumbersome task. You take a compound, make its mirror image, find out whether they overlap or not. Very cumbersome job. So we have made a very simple rule for you. It has been found that organic compound will be optically active. An organic compound will be optically active if it has at least one chiral carbon. It should have at least one chiral carbon. The compound having chiral carbon will be called as a chiral compound, and it will not overlap on its mirror image. But what is chiral carbon? Chiral carbon, definitely it's a carbon. Carbon is attached to 4 groups, and the condition for the chiral carbon is the one. That means all the 4 groups which are attached to this carbon should not be same. They all should be different. Like A, other one will be B, third one will be C, other one will be D. Then this carbon is called chiral carbon, and any compound which has one chiral carbon will be definitely optically active. Let's take an example. As I gave an example in the beginning, that lactic acid is an optical active compound. Let's see what is the structure of lactic acid looks like. It has a carbon. One group is COH, other group is OH, other group is CH3, other group is H. So you can see this middle carbon is a chiral carbon. So this lactic acid, whose isotopic name would be, I think you would have guessed it, 1,2,3,2-hydroxy propanoic acid, is an optical active compound since it has a chiral carbon. So any compound which has one chiral carbon will definitely be optically active. Now you may ask, if it has got 2 or 3 chiral carbon, then what happens? If the compound has got more than one chiral carbon atom, then it may or may not be optically active. For example, I show you one of the form of an acid called tartaric acid. This form of tartaric acid is optically inactive. As you will see the structure, it has 2 chiral carbon atoms, but still the compound is optically inactive. This compound is optically inactive, though this carbon is chiral. You can see 4 groups, all different. This is a chiral carbon, 4 groups, all different. 2 chiral carbon atoms, but still this form of tartaric acid is optically inactive. Because it is a symmetrical molecule, it has a plane of symmetry. Any molecule which has a symmetry can never be optically active. But definitely, if a compound has got one chiral carbon atom, 100%, it is going to be optically active. Don't worry, we are not going to discuss in class 12 the compounds with more than one chiral carbon. So at our level, we can say at the NCERT level, the compound which has got one chiral carbon will be 100% optically active. And just for your knowledge purpose, this one is called mesotartaric acid. And let me explain you why this compound is optically inactive. If you pass a polarized light through it, what happens? The upper part of the compound is going to rotate the polarized light towards right. The lower part of the compound will rotate the polarized light towards left by the same angle. With the result, net rotation of the light will be 0. So this form of tartaric acid, which I told you is called mesotartaric acid, is optically inactive, though it has got 2 carbon. But don't worry, we will not discuss those cases. We will discuss only compound with 1 carbon like lactic acid, which is 100% optically active. And since it is an optically active compound, what it will do? It will, when you pass polarized light, this form of lactic acid will rotate the polarized light either towards right or towards left. It may be dextro, it may be levo. We cannot see the structure and find out whether it is dextro or levo. That we have to find out experimentally. Okay, by looking at it, I can't tell you whether this is going to rotate the polarized light towards right or towards left. So what are optical active compounds? The organic compounds which have at least 1 chiral carbon. Chiral carbon means the one attached to 4 different groups, and the compound which has a chiral carbon is called as a chiral compound, and it is an optically active compound. Now let me give you a very simple question as a classwork to do. Can you give me the structure of the smallest alkane which can be optically active? Try to draw the smallest alkane which is optically active. Smallest alkane which is optically active. Now how do I draw the smallest alkene? I am supposed to use only carbon and hydrogen. I put a carbon. The smallest group I can attach to this carbon is H. The bigger one, CH3. More bigger I can put is C2H5. Even more bigger is C3H7. So this is the smallest alkane which can be optically active, and this is a chiral carbon. And what is the IUPAC name of this compound? This will be a long chain with how many carbon? 2, 3, 4, 5, 6. Hexane derivative. 1, 2, 3. Third position methyl group. So the compound is nothing but 3-methyl-hexane. This is the smallest alkene which can think to be optically active. Methane cannot be optically active because in the case of methane all the 4 groups will be same, that is the hydrogen. Now let's see the smallest alkene which can be optically active. So again C, we can put a group H, next higher group CH3, we cannot repeat. Another group C2H5, but we have not put a double bond till yet, so we can put a double bond CH, double bond CH. So this is the smallest alkene which can be optically active. This middle one is a chiral carbon. What will be the IUPAC name? 1, 2, 3, 4, 5. So it's 3-methyl-pent-1E. So this is 3-methyl-pent-1E is the simplest alkene which can be optically active. And I think by drawing all these 2, we can even draw the smallest alkyne which can be optically active. Same thing, just instead of double bond, we'll put a triple bond. So it will be C, H, CH3, C2H5, and this is C triple bond CH. That is your 3-methyl-pent-1-ine. So all these are nothing but optically active compound. Why they are optically active compound? They all have 1 chiral carbon, so they will be optically active. What is chiral carbon? Attached to 4 different groups. If they are optically active, what does it do? If you pass a polarized light, they will pass the light, rotate the light of the plane of the polarized light either towards right or towards left. The one which rotates towards right is called dextro, the one which rotates towards left is called levo. Dextro is represented by the symbol small d or with a plus sign, levo is represented by the symbol small l or with the sign of minus. And I cannot tell you these particular forms, which 3 forms I drawn on the blackboard, whether they will be dextro or levo. That has to be found experimentally. Looking at the structure, you cannot predict whether it is dextro or whether it is levo. So I think by now you are clear about what are optical active compound and what do they do and how to find out. The compound definitely should not have any symmetry and it should have at least 1 chiral carbon if you are talking about organic compound. Even inorganic compounds are also optically active, but in that case then there will be no carbon. We will check about its what you call overlapping criteria. It should not overlap on its mirror image. So after we are clear about what are optical active compound, we will now discuss a special type of isomerism shown by optical active compound called optical isomerism. Another term for optical isomerism is nothing but it is called enantiomerism. This type of isomerism is only shown by none other than optical active compound, the one with a chiral carbon. This is an example of stereoisomerism. Like in 11th class we have done another stereoisomerism called geometrical isomerism. You remember cis and trans. So this is also an example of stereoisomerism. It is not a structural isomer. So this is an example of stereoisomerism shown only by optical active compound. Optical active compound is the one which shows this type of isomerism. And in this isomerism, given optical active compound can exist in two forms. You will be able to make only two isomer of the given compound. Two forms. One form will be object. Other form that I can draw will be its mirror image. I will draw an object and its mirror image. These two will be called as optical isomerism. The two forms that I draw, or the two isomers that I draw for the given compound, both will have same molecular formula. They will have same physical property like boiling point, melting point. Their chemical properties will also be same because they will be having the same functional group. Only difference will be that if this form will be dextro, rotate the polarized light towards right, this form will be levo. Or if this is levo, this has to be nothing dextro. So optical isomerism, also called enantiomerism, and of stereoisomerism, possible. Another one will be its mirror image. This is what is lactic acid, optical active compound with one chiral carbon. IUPAC mean 2-hydroxypropanoic acid. So I can draw two optical isomers. One will be an object, another one will be mirror image. Mirror image, what will happen? The group on the right will become left and the left will become right. They will interchange. So its other optical isomer will be this. So these are the two optical isomers I can draw for lactic acid. They both have same molecular formula. You can put any group anywhere, that is not a restriction. They have same molecular formula, same physical property, same chemical property. Only difference is if this is dextro, this will be levo. If this is levo, this will be dextro. It will have a rotation of plus 50 degree, this will have a rotation of minus 50 degree. Now let us draw optical isomer for simplest alkane which is optically active. Remember simplest alkane which was optically active? It was like this. We just discussed 3-methyl hexane. So how do I draw optical isomer? Just make its mirror image. Its mirror image will be like this. So optical isomerism is very simple. You have to just draw two isomers. You don't have to draw 4 or 7 or whatever. And only thing is that one isomer is object, other one has to be its mirror image. Right will become left and the left will become right. So these are nothing but optical isomers. As I told you, optical isomers of the given compound have same molecular formula, same physical property, same chemical property. Only difference is one is dextro, other one is levo, another one is levo, this has to be dextro. And which one is dextro, which one is levo has to be found experimentally by looking at it. You can't find whether one is dextro, another one has to be levo. How do you find out? By doing the experiment. Lastly, I would like to discuss with you a term called racemic mixture. I like to discuss with you a term called racemic mixture. These terms we'll be using later on these particular terms when we do the chapter called haloalkanes, haloarenes, starting from tomorrow onwards. So we are discussing the last term for the class. What is racemic mixture? Racemic mixture is basically, as the name suggests. Now suppose you have got 50% tartaric acid molecule of this type. Suppose we have got 100 molecules. 50% molecules of tartaric acid are of this type. And 50% are of this type. As you are clear, basically what is there is that we have, suppose 100 molecules, 50 molecules are of this type and 50 molecules are of this type, lactic acid. So we have got lactic acid, 15% molecule of this type, 50% molecule of this type, 100 molecules, 50-50%. What's the difference between these two? These are the optical isomers. One is dextro, other one is LIGO. If you pass through this mixture, the polarized light, what is going to happen? You will find if this particular 50% molecule try to rotate it towards right, the other 50% molecule is going to rotate the plane polarized light through the same angle towards left side. So with the result, what is going to happen when the light is going to pass through it, it will remain as it is. It will not either go towards right or not towards left. They will neutralize their effect and all that. So this mixture is called as nothing but the recipe mixture. So what is the recipe mixture? Recipe mixture is a mixture which contains 50% dextro form, 50% LIGO form of the same compound. It's a mixture which contains 50% dextro form, 50% LIGO of the same compound, and the mixture is going to be optically inactive. Why optically inactive?